Okay, so for the first one, we're basically just doing PMP type of junction. So what you're going to see, this is used in transistors. And so the big thing for us to remember is that whenever we have a transistor, it can be separated into three regions here. And so basically, this first region here, it's more heavily doped, what we like to call, so I just say P plus. The middle region here is going to be Rn, so the other type material where the electrons are. And then the third region here is just P. And then what's going to happen is between the heavily doped and the N junction, it's going to be forward bias. And so we're going to see that there is just a small region for the depletion region where the N to P, it is reverse bias. So then it is a large, basically, junction there. And what's going to happen, we're going to see is we have the emitter terminal on the side because it emits the charge carriers. And then we have the base terminal here in the middle, and then we have the collector terminal on the right-hand side. And let's think about it. If what's being emitted in the heavily doped P region, that must mean holes. And so they're going through, and remember, diffusion's made easier in forward bias, so there's a lot of them coming through here due to diffusion. So we can just represent the holes here. And this one is due to diffusion. And then what happens here is they're going to go through, and you need to recall that within a PN junction, because we have our reverse bias here, the depletion region's pretty large. So within here, we have our electric field created due to the large depletion region. And that's because some of these holes basically come over to the N side, some of these electrons go to the P side. And so what's left behind is these dopant ions. So here we're going to have pluses for dopant ions, and here we're going to have negatives. And remember, an electric field's created from positive to negative, so that's where the electric field exists. And so therefore, once these holes just land in here, they're going to be dragged by the force of the electric field. So therefore, we can have our arrow just keep going through. And this one is due to drift here. And that's because it's in the presence of an electric field, those charges. And now that we talked about that, we need to talk about the type of currents in there that are being fed back into the device. And so what's going to happen is, because we have holes, what about the direction of electrons? Because we could tell in this PMP, the holes are able to move throughout it. But what about the direction of electrons within here? And so the electrons are going to go basically from the base, and there's going to be some holes that drop down here in the base region from the diffusion. Not all are going to go through the drift process. And so some of this current here that's coming through the base is going to go up for recombination. So that's where we might see an electron here combined with a hole. And then the other current is going to go here. And so why is it going to go to the left here? Well, it's going to go to the left because some of these electrons are going to diffuse over. However, the diffusion rate is a lot less for these electrons. And the reason it's a lot less is because there's a larger concentration of holes here. It's about 10 to the 19th. That's what I like to think of this number. In the middle, it's going to be about 10 to the 16th. And then over here, it's 10 to the 15th. And that's your approximate numbers. And so what you can say then about this is that since there's so many holes here, there's about 1,000 more holes than there are electrons due to the order of magnitude of 3. So for every 1,000 holes that are moving from the P to the N, there's only one electron moving from the N to the P. And so that's why there is a little current supplied to make up for that diffusion loss of electrons here. And then electrons that are recombining with the holes over here in the base region. And then the third current we have is going to be these electrons going over. So basically, due to our drift, is what's going to happen is they're going to fall in and they're going to come over to the other side. We like to call this the leakage current. And so he has a specific name for each of these currents that he follows. And within his notes, he would often talk about it. And he said, the total current that's supplied to the base is equal to IB1 plus IB2 plus IB3. And so, the only issue here, though, is we're going to see that we need to actually subtract one of these, move it over to the other side, because one of these currents is actually coming in while the other two are going out, and he made the same error when he was writing this out. But you'll see that the current that's going to the recombination current is going out from the base. The current that's going to, due to diffusion, is going out from the base, but the current that's coming into the base is the one due to the leakage current. And so this one's actually a minus here. So what you need to represent this with is a minus sign, so minus IB3. And so if we're going to define each of these, this is the leakage current, as we said. IB2 is going to be our current that is due to diffusion. And IB1 is going to be our current that is due to recombination. It doesn't matter, IB1, IB2, however you label it, just so you know what each one represents. That's what you could call this IB1, the other one IB2, and the other one IB3. They're just arbitrary, so you just need to know what causes each of these currents. And then this is the base current, of course. And now that we talked about that, we're going to look at the charge concentration model. And so the charge concentration model, what that looks like is basically within our junction up here. I'm going to draw it below it. And so we're going to sort of see how they represent the charge carriers. And so here we're going to have basically the junction. So let me try this measure. Okay, so we know in the heavily doped P side, that's of course going to have more holes here. And so what we're going to see is P is going to equal 10 to the 19. And let me get a better marker for that. The one down here, this is going to be our N. So our N, it all adds up to 10 to the 20th. So the N here is going to be 10 to the 1. So the concentration of electrons in that heavily doped P side. And then we're going to have the N side, where of course there's going to be more N, but it's not as heavily doped. So N equals 10 to the 16th. And then P is going to equal 10 to the 4th. And then on the right-hand side here, it is even less doped. And so it's P equals 10 to the 15th, N equals 10 to the 5th. So now that we have those three layers here, we need to see what is the charge carrier concentration? How is it going to change? And so basically what happens is, let's just start from the basic point. So due to these holes that are moving from the P to the N side, there's going to be a lot that are going to go over and they're going to be able to make it to the other P terminal. So they started from the emitter and a lot are going to go to the collector. And so how are we going to represent that? Well, if we have a lot of P holes coming into the base, I'm going to draw it up higher here because there's a higher concentration of holes than I marked down here. And the base is made really small. So it's really hard for those to recombine. So it goes down only a little. And that's what we're going to see. So because the majority of them go to the collector, basically all those holes that come in here, there's very little change because only a few recombine. Then the other one that I'm going to draw is those electrons that are coming over. There's not as many electrons that are able to diffuse the other way. So maybe I should do this in the other color I use for the diffusion of the electrons. But they're going to return to their equilibrium value because there's a lot larger space in this heavily doped P region of the emitter, because the emitter is a lot larger. The base is made thin and narrow, so therefore it's harder for it to recombine. But the emitter is larger than the base, so therefore there's more distance for this electron to recombine and then finally return to its equilibrium value. And then over here, what are the charge carrier concentrations of these ones? And so what we're going to see is, of course, there is going to be, if there's a lot of these holes that are able to make it over to the right-hand side here, we're going to see that there's going to be a lot less electrons in the collector. So that's why he wrote it down here. He said something like 10 to the negative 2, because there's a lot less electrons in comparison to holes if a lot of holes are able to make its way over into this P region in the collector. And then here in the base, what is brought down more? Is it the amount of electrons or is it the amount of holes? And so what we're going to see is that basically very little of these holes are in the base region to begin with, and very little recombine in there. And so we're going to notice that it's going to bring this level down too as well in the base. We're going to have like 10 to negative 3 or something. And so that's what he just tried showing through the charge carrier concentration diagram, was how specifically these charges are going to move and how they're going to affect the concentration in each of these equilibrium values we had to start out with, and how it looks a little different. And so that's what we had. But basically, if you just have more forward bias, you're going to have more diffusion, so more of these holes can make it over to the collector terminal. And so one cool fact is that, so just like a little one that's nice to know, we use NPN transistors. And the reason why we like using them is since electrons move faster. And remember the mobility of holes versus the mobility of electrons. The mobility of electrons was like 1350, and the mobility of holes was like 480. And there's some units to that, but I forgot them, and you probably did too. But it just shows you that electrons are more mobile than holes, and therefore they make better transistors because charge carriers are moving at a faster rate in comparison to holes. So it can happen faster. The amplification, if you're using a BJT or a switching mechanism, the results you'll get will occur in a faster period of time. And now that we talk about that, let's get to, basically, I want to label the transistor because I feel like the parts of it we label, but we don't know what they actually mean when you go to labeling a transistor. And so when we start out with our normal transistor, we can have two types. We can have a PNP, or we can have an NPN transistor. And so what's the difference between them? What I always like to think of is the PNP. We know it's going to be heavily doped with holes because we have the heavily doped region, then the base, then the collector region, where the NPN, it's heavily doped with electrons since our emitter region is heavily doped, and then the P is the base, and then the N is the collector terminal. But what's nice to know is I always like to think of the middle term. For the PNP, it must be a negative voltage is supplied here. supplied for VCC, where your NPN, it needs to have a positive voltage. So I always think of that middle term. Positive voltage supplied for VCC. And now that we talk about that, that's just my little mechanism to know what's the correct configuration. But we also need to think of the symbol, because a lot of times we see the circuit symbol and we're like, ooh, is this an NPN or PMP? And so here's the symbol for a BJT that we often use. And so which direction should the arrow be pointing? Well, the arrow should be pointing from the positive to the negative. And we know electrons are in the N region, and so holes are in the P region. So that's where it's more positive, is in these P regions here. So basically the emitter, what we need to think is this is always our base, then we have our collector, then we have our emitter. I like to keep the configurations the same when I draw the symbol so I don't get confused. And if it goes from positive to negative, a diode, how we like to think of it between the base and the emitter, there's a diode drop. It's going to go from basically a diode, remember, it only can go from the positive to the negative, the current flow. It can only go in one direction if we're not zeroing. And so therefore here, what we're going to see is the N to P from the base to emitter, you're going to notice that it's going to go from a negative to a positive. So therefore, the direction of the diode must be reversed. So it's going to point inwards. And so it can go from a more positively emitter to the base, which is going to be negative. So the direction of current flow. Whereas in the opposite configuration, we're going to notice that the arrow points outwards. I should have probably drew it down here, the arrow actually, to point more towards the emitter. So let me fix that. But the reason is because that diode drop needs to remain from the positive to the negative charge. So let me just fix that real quick. And so we're going to see specifically that diode. It's going to point from our base, which is positively charged, and it's going to go to the emitter, which is negatively charged. So it's in the correct configuration so that there can be a current flow. And now that we talked about the two types of transistors, let's just know how they look, because I feel like a lot of times we don't know how the transistor particularly is labeled. And that's one point the teachers just inferred we knew, but we really didn't know how to start out with what is basically a transistor and how do you label it. And so what I'd like to do is just heads up, transistors can have two types to them. And transistors are either BJTs or they are MOSFETs. So it can be one or the other. BJTs are known as amplification devices. An example could be a microphone. And then your MOSFETs are switching devices. Your BJT is skinny. It looks something like this. It has 3 pins to it. Usually the base is in the middle. And what I tended to notice most of the time, the emitters on the left and the collectors on the right, but you can do the simple test to figure out which one's which. Depends specifics, but we always know the base is in the middle. Our MOSFETs, we haven't dealt with them yet, but they have something, it looks like this, and then it has 3 terminals here. It has a place where you can put a screw in it. And the reason why is this is called like attaching to like a heat sink or something. That's what you want it to do, is because it's switching on and off. It gives off a lot of heat. So therefore you want to connect the screw in here and screw it into like a heat sink or something. And then it has 3 terminals as well. And so it has the base collector and emitter, However, we have not learned specifically which one of those are because we've been focusing on BJTs. And so for our continuation, why we like using transistors is because they do a lot in our circuits. They can amplify a small signal, which you see through microphones, and they can switch something on and off. And so that's why we like using these in a lot of circuits. And so let's go to the basic labeling. So we're going to be focusing on BJTs, not MOSFETs for the rest of this lecture. So for the DC model, which basically means DC model here, what does that mean? It's how does the transistor work for fixed values of currents and voltages. And a lot of the times, the current that we're interested in is IC, and the voltage we're interested in is voltage collector emitter. And the reason why we're so interested in those two is because of biasing. And the DC model is one way in how we can solve for IC and VCE in order to make sure we bias the transistor correctly. And so I will introduce the concept of biasing right after I talk about the DC model a little, because I feel like that is an important part to touch upon. So the DC model, what it looks like is we have our modern transistor for BJT. How we're going to connect up our circuit is usually we have a resistor at the base. So this is usually called RB here. This is a resistor at the collector terminal, RC. We have our transistor here. And then we have this side, the emitter, which is connected to ground. And so let's just try figuring out how do we label this transistor and why is it built the way it is. So here's the power supply to the transistor. So that's what we call it VCC. It's connected to both, you can tell here, this is where the collector terminal is, and this is the base terminal. So it's supplied to both the base and collector. And there's a resistor for the collector and a resistor for the base. Reason why we only have one supply is because it makes it cheaper. We don't need two voltage supplies, because most of the time you could see like a voltage supply to the base and a voltage supply only for the collector. But that costs more money to have two different voltage supplies. So that's why we only like having one voltage supply. Now that we talked about that, there's a resistor at the base and resistor at the collector. So the resistor at the base, that's going to be because we're going to have a base current flowing through here. So I base. And then we're also going to have a collector current flowing through the device. And remember, within a transistor, we're going to want a lot of that current to flow through. The base is sort of like a valve for this transistor. And so now that we talked about that, let's talk about how do we label it specifically. And so between the base, which is right here, and between the emitter terminal, so the base is right here, the emitter is right here, how do we label this section? This is the voltage between the base with respect to the emitter. And so the first letter is just where that's basically your other point, where the emitter is your reference terminal. So the second one is always your reference. And so the emitters are reference here, and there's going to be a diode in between here. And so usually we like to say the voltage between the base and emitter is going to be 0.65 or negative 0.65, depending on the type of transistor you have. And here we can see it goes from a positive to a negative because it's a diode drop. And so it goes from a positive to a negative. So therefore, this must be an NPN transistor. And so we determine our transistor type, which is NPN. Always look at the diode drop, and that will tell you what type of transistor you're working with. And the most common NPN one you work with is the 3904. And so I'm just going to write that over here. That's the typical one that we see in the labs a lot. And now that we talked about those two, we have the voltage between the collector with respect to the base. And what points does that reference? The voltage, basically VCB, is going to be from the collector terminal with reference to the base. And so this is what VCB refers to, the voltage between these 2 points here. And then another important one you're going to see pop up a lot is this final one over here, which references the voltage between the collector and the emitter. So this is called the voltage from the collector with respect to the emitter. And that references from this top point here down to this bottom point. And so that's the specific ones. You just need to know how to label them because the second letter is with reference to. And so now that we know how this specific transistor works, we're going to write a few equations from it. And so let me just redraw it so it's cleaner without all those labeled. And so here, what's going to happen is if we're trying to find, let's say, the voltage on the base resistor, what is that going to be? Well, we know here the voltage on the base resistor, that's given right here, voltage on the resistor of the base. And so that's going to be between the VCC and this point here. Well, what can we label this point? Well, that point there is between the base and with reference to the emitter, so we can call that VBE. So the voltage between is going to be VCC minus VBE, and that is going to give us the voltage drop across the resistor. So that's why I can write voltage across the resistor at the base is equal to VCC minus, and then it's going to be VBE. And since this is an NPN transistor, we know that this voltage drop is in particular 0.65. And so therefore I can just 0.65 is what you could substitute in for voltage between the base and emitter. Now that we know this one equation, another one that's commonly asked is what's the current for the base? And so the current for the base, that's given by what's going through to our base terminal. Well, don't we have a voltage and a resistance? So it's just the voltage of the resistor and the base all over the resistance of the base. It's just Ohm's law, which is equal to the voltage supplied minus, and then the voltage of the base emitter all over the resistor of the base. Because that's what we just derived up here. Voltage resistor base is equal to these two, so you can substitute it in and divide it by the resistance. And then the resistor, the collector, RC, is going to be equal to the power supply minus, and then the resistor, the collector, it's from VCC, and then this point right here. These are the two that are between it. So this point is between the collector with respect to the emitter. So it'll be VCC minus voltage from the collector to emitter all over the current that is supplied through the collector. And so that is our relationship there because we find the voltage drop. This is basically the voltage drop across the collector resistor, VCC minus VCE all over IC. And now that we have these three big ones to find, the one that you'll see pop up is this other one, which is VCE is equal to, and then it's VCC minus ICRC. Reason is because if you start right here, VCC, and you minus whatever voltage drops across this resistor, you're going to get at this point VCE. And so those are the iconic ones that you're going to see mostly used with transistors of what to solve for. And so now that we talked about the DC model a little bit, let's talk about biasing in general. So why do we do biasing? Well, there's three types of biasing. There's simple biasing. There's stabilized biasing. And finally, there's a current source. And so what we like to say for simple biasing is that the reason we don't like it is because it varies directly with beta DC. And you're going to notice that beta DC changes with temperature. And so therefore our transistor is very sensitive to any changes in temperature. And then for stabilized biasing, it basically works, but it does have some limits. And you're going to see that we're going to use stabilized biasing with small signals. So this is for small signal as well. And the current source we haven't covered yet, but those are just the main two types of biasing that we go over in this course, the simple and stabilized. And so why biasing? So biasing, basically the purpose now, finally defining it after talking about it, is basically to establish a stable operating point. Your operating point is sort of like the Q point. And so what is the Q point? So the Q point, defining that, it's basically the best point for operation of a transistor. For a given collector current. So what you want to do is you want to set, so the goal from biasing, so goal for biasing is, what you want to do is set the Q point such that the transistor does not go into saturation or cut off when a signal is applied. And now let's just do some graphical images to actually understand what I mean by all this. And so let's just do a little recap. So within biasing, there's two types we like to focus on, which is simple biasing where it varies directly with beta DC, and that's temperature dependent. Stabilized biasing, which works because it's not as much reliant upon temperature, but it has limits. And this is used usually for small signal analysis. And then biasing establishes a stable operating point, and that's referred to as the Q point. And then the Q point is the optimal point. Basically, for any given collector current, what this means is that that Q point is going to keep it in active mode. So it does not fall into saturation or cutoff mode. And the goal for biasing is in order to set the Q point such that our transistor does not go into saturation or cutoff when a signal is applied. What this basically means in general is transistor remains in active mode. Okay, so now that we got that and we defined all of it in particular, we're going to see now a visual representation of it. And so for our biasing, you guys will probably remember these types of curves. We did them in lab, so they're good to know. Looks something like this, and we have the collector current, and then we have a graph of the voltage between the collector and emitter. And so what this is basically had a lot of these characteristic curves. They look something like this, where let's those were our characteristic curves. And what this is trying to show us is that if we drew specifically a line that goes from the max point to the minimum point. And so the maximum point for IC would be, in particular, it'd be something like, I'm going to say around here. So this would be VCC over RC. That's the max IC can be, is at this particular point here. And the maximum for the voltage from the collector to emitter would be VCC. So if you make a line between the two, that gives you your Q point. So you can see something like that, but it's not perfect. You can look up for a better diagram of this, but it's just like an example. But this is our Q point here, where the two intersect along our characteristic curves. And so a big thing to know is that the different modes of operation. And so within your transistor, the point leading up here, this part is called the saturation mode. And then the next part, where it's actually an active mode, that is all along that flat line. And so you're going to notice that, let me just circle them. This is our active mode. And then down here at the bottom, you'll notice this is where cutoff occurs. So in this lower portion here, you'll see it on the curves when you search it up. That is the cutoff mode. So those are the three different mode types that you're going to have mostly. And so now that we talked about those, what we're going to have is, let's see the four different ones, but all I wanted you to take away from this is how you can see Q point depends on IC and VCE from this graph, because it's IC as a function of VCE. And so you can see the Q point, which is the intersection along this characteristic curves. It depends upon these two factors. Okay, so now that we talked about that, let's get a little into the types of modes it can fall under. And so I like always organizing these graphically. Oh, I forgot one last thing from this graph here. That fourth mode, which is the inverted mode, you don't see it usually on graphs. The reason is because it actually comes down and it goes this way. So right here, it's in the inverted mode, it comes downwards and it's sort of like inverted from this one you can think of. It looks like an odd function. That's what your inverted mode refers to down here. We just don't use it a lot at all because a transistor is not normally meant to be an inverted mode. Because if you're in inverted mode, it's just going to be a lot less. It's basically your NPN transistor. You're trying to make it function almost as like a PNP. And why would you do that? You just use a PNP transistor. You know, like if you're using the opposite charge carriers to flow, you should just use the opposite type of transistor. You shouldn't force one type to act like another one. And so now that we talked about that, let's look at the 4 different modes in our graphical representation. So we can have active mode, which is one type. We can have saturation mode, which is the second type. We can have cutoff. And we can have inverted mode. So those are the 4 types of modes our transistor can be in. And they depend upon the configuration of the base to emitter junction and the base to collector junction. And so what we're going to see is that our base to emitter junction, that refers to our diode. So it's the diode forward bias. If it's forward bias, we're going to see it's going to be in active mode, but it can also be in saturation mode. But if it's in reverse bias, it's going to be in cutoff mode or inverted. And then for active mode, remember the base to collector junction is reverse bias. That was what we drew. Oh, let me get the diagram. These are active mode referred to the forward bias between the base and emitter here, and the reverse bias between the base and collector here. And so that's what I said right there. And remember that inverted is the opposite of active, so you can just sort of think of it as flipped. And then saturated and cutoff. Saturated, they're both forward bias, but in cutoff, they're both reverse bias. And so those are the 4 types of modes your transistor can be in. So how do you know if it's in active mode or not, your transistor? Because a lot of the times you're questioning, is my transistor in active mode or is it saturated? Because those are the 2 modes it's mostly in. It's in one or the other. So Dr. Ari likes to use a little bit of a relationship, which is a little trick that he told me to look at, but then there's another way you can do it as well. And so I like going by the transistor is in active mode if IC max is greater than IC, but in saturation mode if IC max is less than IC. And so what you just need to remember is IC max equals VCC over RC. And so that's the main thing we have here is this is sort of like your little clue to know, is my transistor operating in active mode or not? I always do this check when I start out a problem and I see, is IC max greater than IC? If so, it's in active mode. But if not, it must be in saturation mode. And so let's do an example of the DC model. So let's flip over to some he provided for us, and let's just go over it real quick. So I think we did this one, for transistor biasing. Okay, yeah. Let's look at number 1A in particular, and then we'll look from there. So I'm going to put this on the left-hand side, and let me put this on the right-hand side. Let's do some examples from his sheet. And so for the first one, you can see it gives us a transistor. So my first piece of advice would be identify what type of transistor this is. And so let's just work it out, and we'll see what type of model it is, and then which mode it is in. So what I see here is it says find IC and VCE if beta DC is equal to 200. So it gives us a beta value. And immediately when you see a beta value, you know it's simple biasing because the beta value is known. If the beta value is not known, then you're going to have to use a different technique. And so we can use simple biasing here. And so to find our Q point, what's basically going to happen is when I draw this transistor, which is given by 1 mega ohm here, and we have 100K here, and we have 10 volts at the top. Okay, so we know the beta is 200, and is this an NPN or PNP? Well, I would say it's an NPN because it goes from a positive to a negative, that diode drop. And so we know it's an NPN transistor, so there must be a positive voltage supplied, which there is a positive voltage supplied. And now let's look in particular, how are we going to solve for IC? So to solve for IC here, it's going to be equal to VCC minus VCE all over RC. And so that would be from this point here, from between these two voltages divided by the resistance, and you should get the current going through it. So what we have for VCC is 10 volts. What about the voltage between the collector and emitter? We don't know what that is, but we can, let's see. Can't we use a different technique how to find the voltage between the collector and emitter? Because there's another relationship we know. So let me leave this here for now. We know the resistor collector is 100K, but we don't know what VCE is. That's an unknown quantity still. We don't know what's the voltage from here down to here. But I do know how to solve for the current going through the base. And do you remember the relationship beta DC is equal to the current for the collector all over the current for the base when we're using our simple biasing technique for DC mode? And so what we're going to see here is that we can determine the base, basically current, if we know our gain, which is given as 200, and we know the current for the base, we can find that by doing, it's going to be the voltage of the resistor, the base, all over the resistance of the base, which is equal to VCC minus VBE all over resistor of the base, which is equal to 10 minus voltage between the base and emitter. There's a diode drop here. So it's going to be minus 0.65. all over, and then the resistor of the base is going to be right here. We see it is 1 mega ohm. And so that's why I'm going to write here 1 mega ohm. When you do that on your calculator, let me do it on mine. What I got is minus 0.65 divided by, I got 9.35. So IB, 9.35 microamps. Now that I got IB and I know beta DC, I'm going to rewrite this. So it'll be 200 is equal to IC all over 9.35 microamps. Solve for IC, you should get IC is equal to 0.00187 amps. So we know IC here is going to be given by this value. Which, okay, that's great. Now we know IC, what it should be within this transistor. Well, what's IC max? So we actually didn't have to do this equation because we knew the relationship given by DC mode. So we never had to find VCE. But now that we know IC, we could find VCE very easily. And so let's go though and try finding IC max to see if this is an active or saturated mode. Well, IC max, remember I told you guys it's VCC over RC, which is going to be equal to 10 volts all over 1 mega ohm. Oh, sorry, 100K, using the wrong resistor. And so 10 divided by 100K, I got 1 e to the 4th. And so 1 times 10 to the negative 4th. So if we're going to think about that, what that's going to be is it's going to be 0.1 milliamps. And so that is equal to 0.0001. Yeah. And so 0, 0, 0. And so now let's compare IC max to IC. And so when looking at that, let me make this full screen again. When we're comparing the two, what we're going to see is that IC max, let's see here, we have 0.0001. Here we have 0.00187. And we can tell that IC is greater than IC max. And so therefore we are in saturation mode. So here we are in saturation mode. And so if we're in saturation mode, what that means basically is from our DC curve here, we are not in the active mode region, we're in this buildup region. And so if we're in this buildup region, what's going to be given for IC then? Well, IC will just be, let me do this in a different color since now we're in saturation. IC is equal to beta DC times IB, which would be 200 times, and then since it's in saturation mode, only the leakage current will pass through. And the leakage current was something around like 2 nanoamps when we measured it in lab. And so this would be about 400 nanoamps. It's very small, the current that's going through. It's not even that much since it's in saturation. Now let's talk about what's VCE. Well, remember VCE is equal to VCC minus ICRC. And so that's going to be 10 minus 400 nanoamps times the resistance of the collector, which is 100 kiloohms. So let's do that simple subtraction, 10 minus 400 nanoamps times 100 kilo ohms. I got 9.96. So let me just write that over here since I ran out of room. 9.96 volts. And that makes sense that that is the voltage drop across there because there's such little current going through here in saturation mode that most of the voltage drop will be across the transistor. And so now that we got those two values, that shows you when it's in saturation mode. Now let's do one in active mode for a contrast to this, just to see what different values we should get. And so going to another example here, let's just do the one next to it. I believe that one was active mode. And so looking at his next one, it said he had, oh, okay, so he flipped it here. This is actually a good one to look at. It is 400K. Then he had a 1.2K. And then the transistor looks like and so how would we go about solving this? Well, first we gotta determine the transistor type. This is NPN, so that's great. And when we should be solving this, what I should notice off the bat is that I don't want to work with negative voltages, right? Because this is an NPN, we should be dealing with positive voltages. So therefore, I'm going to redraw this circuit because I'm going to make this, which is right now at 0 volts. Okay, right now, think of a building, 0, -6. Isn't that the same thing as saying 6 and 0? It's the same potential, right? It's only 6 units. And so that is the exact same notation. So we can just redraw this as 1.2K, 400K. Zero volts here and 6 volts supplied. And now that we got that, what we're going to do is we need to solve for IC and VCE. And we know this was an NPN transistor, so it makes sense that we have a positive voltage at top. So that's a good sign. But let's solve for IC. So remember what I said from before. We have the beta value known of 200. So remember they gave it to us. They're like beta DC is 200. That should be like, oh, beta values known, simple biasing, let's do DC mode. And so what's going through your mind right now is how do we solve for this? And so what I would do personally is we need to see, is this active mode or saturation mode? So let's see, IC is equal to beta DC IB. So we know this is 200. To solve for IB, it's going to be the VCC minus voltage between the base emitter all over the resistance of the base. And that will give you voltage over resistance, gives you current. So this will be 200 times 6 minus 0.65 all over. And then resistance of the base is 400K. Which would be equal to, let me plug this into my calculator, 6 minus 0.65 divided by 400K times 200. I got 0.002675 for my IC. That's great. Now I need to find IC max. That's equal to VCC all over RC, which is 6 volts all over resistance of the collector is going to be 1.2 kilo ohms. So let's do that. So our IC max is going to be 0.005. So is IC max or is IC larger? Well, let's see. What I have here is I have 0.002675. Here I have 0.005. And so we can tell that the one on the left is larger. IC max is larger than IC. So therefore, it must be an active mode. So since it's an active mode, IC is actually equal to the value we got. So that's a value for IC right here. VCE is going to be equal to VCC minus ICRC. And that would be 6 minus, and then IC would be 0.02675 amps. 2 ohms. Equal to, and let's solve this. I got 2.79 volts. And that makes sense since we have an actual current going through here. Multiplied by this, there's going to be a little bit of a voltage drop. So the voltage between the collector and emitter, it makes sense that there's about like 2.79. Okay. Now that we talked about that, and we know the difference between active mode and saturation mode and how to tell when it's in one or the other for the DC mode in particular with the given beta value. We've been dealing with DC this entire time, so I'm going to go over real quick what the DC model should look like, but then we need to get into the actual stabilized mode for BJT, because the stabilized mode, that's what you're going to see more often used later on, because stabilized mode is used for AC mode. And right now we've just been dealing with DC, which has been great, but now we have to deal with AC, which sucks. And a lot of engineers do not like AC mode. Okay, so let's just finish off the DC mode because I feel like we need to talk about this real quick before we can move on. Is how would you represent specifically when it's in DC? And so we have our 3 terminals here of our transistor. We have a collector, we have an emitter, and we have a base. And so what we're going to use is the amplification factor. What we represent for that is because it's dependent upon beta DC IB for our collector current. That's why we use our dependent source. It's dependent upon our beta value. And then we have some leakage current here. So this is ICEO, which is the leakage current that is in our transistor. Remember IB3, that's where this one's coming from, sorry. So we can write this under leakage current. And then our next one is going to be our the diode drop here. And so within our diode drop, what we do have is between our base and emitter, there is a diode drop. And then there is some resistance due to the contacts, but we usually ignore the resistance due to the contacts. And that's usually written by RBB, but we neglect that the majority of the time. And then that is what we have in particular for a DC model. But what you're going to notice is what we add into the circuit is we add RC, because we have resistor at the collector. We have usually like some type of voltage between the collector and emitter. So that's where this source comes from. Then we have a resistor connected to the base. So that's where this one comes in. And so that's what we usually add within our circuit. So that's how we change up the transistor model a little bit, because we add two resistors and there's a voltage actually given VCE, which we know is equal to VCC minus ICRC. But what you need to know is just this is what the simple transistor looks like, but this is what we hook up to it. And so that's just what explains all the phenomenon. And now that we have covered this regular DC model, let's get into AC a little bit. And so let's talk about the stabilized model for the BJT. And so the stabilized model, why we like using it is because IC changes very little with beta DC. So it's not temperature dependent. And so that's where we're going to see our transistor. Because we just drew the DC model, let me just show you guys that again real quick, because you'll see why and how it interconnects here. But remember, we had dependent source here, and this was given by beta DC, IB. And we had the independent, which is just the leakage current, ICEO, because the base was open in that. Then we had our RBB, which we ignore. And then we have voltage between the base and emitter, which is due to the diode drop. So that's what we had. And then what we added is, because we have a resistor at the collector, so RC here, and then there can be a VCC, which is applied there, and then we usually have resistor at the emitter, and then usually emitters hooked to ground. And then we have R Thevenin. We're going to see why we use this. And then we have a V Thevenin. So where's this R Thevenin and V Thevenin coming from? It comes from this other model where we have normally our transistor hooked up. So it looks something like this. RC, VCC. In this model, you're going to see this exact configuration, two resistors. So R1 and R2 over here. And then it's going to be hooked up to your transistor. And then this is. So what we have here is basically this transistor, all this part here. Let me do it in a different color, actually. So let me circle this all in blue. Or actually, this represents this transistor here, all the pink stuff up there. And then what we did here is we represented all this through this right here. And so R Thevenin and V Thevenin come from particularly this side of the stabilized model. And so R Thevenin is equal to R1 in parallel of R2 because they both share two nodes right in between, and the other node they both share is ground. V Thevenin is equal to VCC times R2 all over R1 plus R2. Because this is the point where V Thevenin is measured. And so that's how we get R Thevenin and V Thevenin in our model up here. We just take it from the stabilized model. We find our V Thev and R Thev, and we just add it into our circuit. that we had up here for a regular transistor model with the two resistors we add here, and then we find the R thevenin and V thevenin side. So that's how you can derive all this in particular to make sure that you're on track. And so now that we have that, we're going to talk about the next section, which is going to be on how do you derive IC from this? And so deriving IC from this, basically, we did this huge Kirchhoff's current loop to it. And so we started with this equation from this model up here. Dr. Ari started solving it. So it's minus B theb plus R theb, IB plus RBB, IB plus VBE plus RE times IC plus IB is equal to 0. And he simplified it. And when he added all these together, he did IC is approximately V thevenin minus VBE all over the emitter resistor, which is great because you can tell from this equation, it's no longer dependent on beta DC. Unlike our stabilized model, I'm going to put that on the side. I mean, not for the stabilized, for the simple biasing. Remember that IC was equal to beta DC IB, but for our stabilized model, IC is going to be equal to V theb minus VBE all over R emitter. So that just shows the difference. One's temperature dependent while the other isn't. And now that we talked about that, we're going to see the hybrid pi model is oftentimes used to show this relationship. And that's going to be a long derivation. And so I'll walk you through it and why we use the hybrid pi model. However, I do want to introduce some terms here right before we get into it. So let's put these on the side. So for this one, for small signal characteristics, what do we have? Well, this is going to be for voltage amplification. And then we also have current amplification in small signals. Voltage amplification is given by AV. It's equal to the negative V out over Vn. Current amplification is given by AI, which is equal to I out over I in, which is going to be the change in the collector current all over the change in the base current. And that's going to be equal to H lowercase fe, which is equal to beta naught. Recall that beta naught is equal to 1.2 beta DC approximately. And so those are the two types of small signal characteristics that you can have. Now that we talked about that, why do we use the hybrid pi model? Why is it useful? And what do we need to know about it? So the hybrid pi model, it is basically gives us the most voltage gain. That's why we like using it. And so for this, basically what happens is it's used for small signals. And so if we write the relationships here, IC, which we need as a diode specifically, these two, IC is equal to the saturation current, and EBBE, which is the voltage of the diode over VT. And so what we have here, this saturation current is larger than IS in IB. And then we have IB is equal to exactly the same thing, like a forward bias diode. So it's equal to ISE all over VT. And so the only difference here is that we notice that the saturation current, we can keep the same, but the main thing why we like to say this way is it comes from the relationship that IC is equal to beta DC IB, which is equal to, and then if you substitute in for IB what we just had here, ISEVBE over VT, you're going to notice this is where I get my IS apostrophe from, beta DC from IS. So this is where I say IS apostrophe for IC. That's where we get EVB, VT, and that's how we get my IS here. Now that we get that, what we're going to notice is that with each of these curves, remember they look pretty similar, the IC versus VBE and the IB versus VBE. So here for our first one for the IC versus VBE, it's going to look something like this. For the IB versus VBE, it looks very similar. And so what we're going to notice is that because of these relationships, and we know this one though is beta times bigger, beta DC times bigger from this because of saturation current. And what we're going to see though, we're going to later define some terms. And so we're going to get the slopes of these, and the slopes of these graphs are going to correspond with what we have in particular to our equations. And so let's get a little into just seeing the model at once, and then we can go back and define those slopes. And so for the hybrid pi model, what does it look like? We have a base and we have an emitter down here. And so between them, we have an input resistance, which we model by R pi. Notice I'm using lowercase letters here since this is an AC model. And now that we have R pi, it's going to be V pi here. And then we have a link resistance between the two. The link resistance has very high resistance. And so most of the times we don't even take it into account. So I won't even take it into account for anything in this calculation since it's so large. Then we have a dependent current source, which is GMV pi. And that just tells us the size of basically the collector current for the input voltage we have. And then we're going to have the output resistance here. It's going to be R naught. And then here we have our collector terminal, and we still have our emitter since it's sharing the same one, same node. And then what we're going to do is we have a defining equation that relates. So basically our defining equation here is for IC, and it's equal to IS and then EVBE over VT. And then we have 1 plus and then VCE all over VA. And so we approximate this, which we did above in forward bias as ISE VBE VT. Because we forgot about the second term here. We just said that's close enough to 0. And so because if you remember the V of A, it was around like 380 when I did it on mine. And so this is a really small number because this over 380, you can almost make this 0. And so it's just 1 times this for forward bias mode operation. And so the input resistance, let's look at all of these in particular and just understand how we get them and how we come to this conclusion. And so starting with the first one for the input resistance, what is that going to be? The input resistance is given by R pi is equal to, and then notice there's a voltage drop in between here. It's between the base and emitter. So the change in the voltage drop between the base emitter, because we're talking about AC, so that's why it's always the change in, over the change in the current for, sorry, not the current, it's the current in the base. And remember, because this has a high resistance, the link resistor here, this most of the current's going to go through here. So that's why we can just say IV. So it's going to be the change in the voltage over the change in the current. And so, because remember, voltage over current gives you resistance, that's going to be equal to dVBE all over. And then if we look here, this is going to be IC over beta naught. Because IB times beta naught gives us IC, so we can just substitute it in here. And the derivative of the constant beta naught will just come out, so that's why we can just bring out beta naught, and because it's fraction over fraction, but this one could come to a numerator, and it's a constant, so we can bring it out. And then 1 over, rewrite it, so it's DIC over dVBE. And so now if you take the derivative, and we know what IC is. IC, if you recall, we just did it up here. So the derivative of this with respect to VBE, a 1 over VT will come out in front. And so that's how we're going to get, in particular, 1 over VT, and then it'd just be the repeat of this, which is just IC. So that's why I can write here, this is going to be beta naught, and then it's 1 over VT IC, which we can just write as beta naught, and then bring the VT to the numerator over IC. And you can also say beta naught over GM. Because we're going to define transconductance. And transconductance is going to be given by the voltage output over the, the current output over the voltage input. So if we look at transconductance, it's going to be given by G of M is equal to the change in the current output over the voltage input. And so it basically, do you guys know the current output's always IC? So we can do DIC over the voltage input, which is, if we look back up at our model here, the voltage input is V pi. So this is going to be derivative of V pi. And that's the same thing as VBE. V pi is the exact same thing because it's just the voltage between the base and the emitter. So I can write it that way. And if you take the derivative of this, what you're going to notice is that, remember, it will become taking the derivative of IC here where we approximated it with respect to VBE. It's just a 1 over VT comes out multiplied by IC again. And so it would just be IC over VT. That's what we get there for transconductance. Now that we got transconductance and we see how we can relate it to just IC over VT, we see why we just did V naught over GM here. Now that we talked about that, we're going to have the output resistance. So the output resistance is given by R out, which is looking up here at the model, it's between the voltage between the collector and emitter all over the current IC, because that's what's actually going through. And so what we're going to notice is for output resistance, if we write the equation, it's going to be the derivative in VCE all over change in IC. And what that is going to give us is, if we take the derivative, we're going to do 1 over maybe DIC all over DVCE. Reason why is because we can take the derivative of this equation here, which, remember how I told you this is the full out equation? This is where the VCE term comes from. So when you take the derivative with respect to VCE, so you take the huge thing here, VBE over VT, 1 plus VCE over VA. What you're going to get as a result from this long derivative is just, it's going to be equal to VA over IC. And so that's how you get the output resistance. And then your link resistance is gonna, it's so large, it's literally negligible, so I'm not even going to address it because you never even see it. So link resistance, just remember it's really large. And so let's look at the input resistance. Because oftentimes we look at this, and it's going to be R pi in parallel with RB when we draw out the model, which I will do after, and we can approximate this to R pi. And remember, R pi is equal to beta naught VT over IC. And our VT at room temperature, we know this is 0.026. But this can change depending on your temperature you have it at. And then your output resistance is given by R out in parallel with RC, which we approximate to RC. This one we're going to see pop up as well. But what we need to know is this just comes from our model, which we drew in class. So let me just show it above here. When we did a lab experiment and we were looking at this, we noticed that R pi is in parallel with RB, and the resistor that dominates in this parallel configuration is R pi. So therefore, we can just approximate that input resistance, because this is the input terminal on this side. We can approximate it to R pi. The output terminal is given on this side. And so then when we did R naught in parallel with RC, we noticed it was very close to RC. So that's why we can approximate R out to RC. Now that we got that, we're going to do particular look at how do you get the voltage gain, how do you get VCE, and how does it depend? But remember how I said the voltage gain is given by the negative of V naught, V out over V in. And so here we made it a Kirchhoff's loop here, which was the voltage in particular here. And so if we look at the voltage that, let me see, is this going to be the current I out over voltage input? Okay, sorry, this is the current. And so we had the current coming out, and then we had to look at the current going up. And so then we took R out in parallel of RC and multiplied that by this current source in order to get the voltage output, because this current source gives us the current, which is great, but what's the resistance? So we took these two in parallel, multiplied it by the current source to give us the actual voltage that should be read across here. And so that's how we substituted it in for the voltage output. The voltage input, remember, it's approximately R pi. We said the input resistance. So therefore, we know across R pi, we're given the voltage V pi. So that's why we could say here, we could approximate voltage input with V pi. Then we can cancel the V pi's here. So it gives us negative GM, RC in parallel of R out. And then we know RC is the dominant one, so that's going to come out. And then that will be equal to, if we substitute in what we know, GM is the current out all over the voltage input. So that's why we can rewrite it as IC over VT, RC, and then we know IC times RC gives us the voltage across the resistor. So VRC all over VT is what we can also use for our voltage gain. So when we go back to what we wrote down earlier for voltage amplification, you can also write this from this relationship up here. It's negative VRC over VT. And then that pretty much answers all those questions here. And so do you guys have any other questions you want to go over in particular from this? Because I was just explaining the hybrid pi model, why we use it in the AC mode. If you guys have any other questions, share them in the chat or I'll end the recording.